This talk today gives me a certain amount of anxiety because it's different than any other chemistry talk I've ever given. First of all, it's kind of autobiographical, and that's always a little embarrassing. Secondly, it's maybe more nearly the history of science than science itself. However, it is appropriate because we're just 50 years since the testing and dropping of the atom bomb in 1945. Well, let me begin then. With the attack of the Japanese on Pearl Harbor in December 1941, suddenly things were totally different in American universities and colleges. There was no longer a free, relaxed sort of attitude. Suddenly, because of the war, things were really different. I was a junior, a third-year student at Bethany College, which is a small liberal arts college in West Virginia. I was studying chemistry for my major with math as a minor. Now, because I took an overload all the time, in view of the war, it was very easy for me to complete my degree a semester earlier. So I got my bachelor's degree in January 1943. Also, I was a good student. I graduated summa cum laude, the top in my class, and because of this, I received an offer from Harold Urey, to work in the Division of War Research at Columbia University. And of course, I was very excited about that because Harold Urey was a Nobel laureate, having discovered deuterium. Well, when I got to Columbia University, I almost never saw Harold Urey. This is a picture of him, the way he looked when I did know him much better at the University of Chicago after I'd gotten my doctorate. And I'd like to tell you a little bit about Harold Urey, because I want you to get a feeling for the scientists that are involved. Harold Urey was a fairly poor farm boy who grew up in Montana. And he went to Montana State University and had a double major in chemistry and geology. He didn't have enough money to go on to graduate school, so he took a job working briefly, first in industry, but then mostly teaching in high schools, and finally teaching at his alma mater at Montana State University. So then he had enough money, and he went off to the University of California at Berkeley. When I was a graduate student there, one of the little tidbits that people talked about from time to time was the fact that Harold Urey had succeeded in having the shortest Ph.D. dissertation. I don't know the exact size, but it was supposedly only about 10 or 12 pages. Mike says about 30, so you see I was exaggerating. Anyway, while he was there, he learned of a very strange puzzle. People had been doing electrolysis for years and years, and somebody chanced to measure the water that kept being added to this electrolysis system, and they found out that it had a higher density than normal water. And so it was called heavy water, but even with purification, that density continued, and nobody understood. So Harold Urey, in a series of brilliant experiments, was able to prove that what was happening is that the deuterium concentration in the water was increasing. At that time, it was not even known that there was a deuterium isotope. So he discovered deuterium, and for this he won the Nobel Prize. However, I'm getting ahead of myself, and I want to go back now, before I was even a student at Bethany, to about 1934 and 35. At that time, Enrico Fermi was doing experiments in Rome, bombarding uranium with neutrons. And let me tell you just a bit about his reasons for doing those experiments. It was known at that time that if you took phosphorus 31, I think I will start a little bigger, phosphorus 31, atomic number 15, and bombarded it with neutrons, you got a radioactive isotope, phosphorus 32, which is used very much today even in biological experiments. But that phosphorus 32 beta decayed to sulfur 32. Now look what happened. You see, we started with atomic number 15 and we went to atomic number 16 in this procedure. So in an incredibly brilliant but simple idea, Fermi said, what would happen if we took the very highest atomic number that we know, uranium, was the highest then, and did the same process? So his idea was take uranium, let's say 238, 92, bombard it with neutrons, get a radioactive uranium-239, and then maybe that uranium-239 will decay by a beta minus to give a new element with atomic number 93. So his idea was to make a new element beyond the then known periodic table. Simple and brilliant. So that's what Fermi was doing. And what Fermi did was find a whole series of new radioactivities, and they were extremely excited. They called them Eka uranium 1, Eka uranium 2, Eka uranium 3, and they said they were making a whole series of new man-made elements. Well, for this, and for his work on beta decay, Enrico Fermi won the Nobel Prize. Now, it turns out that what he had done was wrong. His interpretation of what he had done was wrong. And we'll look in a minute why that is so. However, what I would like to tell you first is a little bit about Fermi. Enrico Fermi was an Italian physicist who at a very young age became professor at the University of Rome. And for my personal belief, at least in my personal belief, he was the greatest combination of an experimentalist. Here he is doing experiments with tubes and so on, old-fashioned tubes. Theorist, shown here giving a lecture. He was a very good theorist. And teacher. I heard him give many, many lectures. Here he is with his graduate students. That particular one is Segre, who also won a Nobel Prize. Well, however, what I should tell you now is that, of course, all the chemists, particularly the nuclear chemists, were very, very anxious to find out what the properties of these new elements were. Here were all these new elements that Fermi had discovered. They wanted to find out what the properties were. So, of course, they were all looking, and one of the most brilliant was a nuclear chemist by the name of Otto Hahn, shown here. And he, together with his student, Fritz Strassmann, studied all of these elements, quote, elements, which Fermi had made. And they were able to prove conclusively that, in fact, Fermi hadn't made any new elements at all, even though he'd won the Nobel Prize for this. What he had done instead was split the uranium nucleus into two pieces. And one of those pieces, the one that Otto Hahn and his student Fritz Strassmann studied especially, was simply barium. Okay, well, this work was published in January 1939, and it caused a sensation. One of the people working in Berlin with Hahn was Lisa Meitner, shown here. She was a sort of assistant, or maybe we'd call it a postdoc now. And she realized something that Hahn didn't realize, that because the mass of uranium was what it was, and the mass of the two pieces into which the uranium broke were what they were, that there would be a considerable loss of mass, and that mass would have to turn into energy. So she predicted, together with her nephew Otto Frisch, that fission of uranium would create a tremendous amount of energy. Well, it was just at this time that Hitler began to increase his persecution of the Jews. And both Enrico Fermi and Lisa Meitner immigrated. Fermi used his Nobel Prize lecture and so on to leave Italy, and Lisa Meitner, and Fermi went to the United States, Lisa Meitner to Sweden. Well, as soon as Fermi got to the United States, he initiated a series of experiments which were also going on other places to find out if the idea of Lisa Meitner was correct. And he used some fairly simple equipment and showed very quickly that huge amounts of energy were released with each fission, about 200 million electron volts, whereas an ordinary chemical reaction is pretty energetic if it has 1 electron volt. Just at this time, Niels Bohr, shown on this next transparency, skiing at Los Alamos, realized that it was not uranium-238, the main isotope of uranium, but a rather rare isotope, present in only 1 part in 140, which was the species which was fissioning. But since I have Niels Bohr up here, let me tell you a little bit about him. I was fortunate enough to be in his institute from 1955 to 1958 while he was still alive, and I got to know him really quite well. In fact, he offered me a professorship in his institute, and my wife Yvonne and I loved the Danes and were really extremely happy in Denmark, but after thinking about it, we wanted our children to grow up as Americans. Irrational, but that's what happened. Anyway, Niels Bohr was a very athletic man, fairly small with a huge head. You can almost see on that picture, really a very, very large head. In fact, let me tell you a story about that. When he and his brother Harold who was a famous mathematician, were young, their mother took them out for walks and so on, and they overheard another lady saying, "Oh, how sorry she is for that poor mother who has these 2 hydrocephalic children. They didn't have so much water in their heads as they had brains." Okay. So I should also tell you, I guess, that Niels Bohr was on the national Danish soccer team. He was a very, very good athlete. In addition, he was a very kind man. He used to always invite the children of the guests at his institute to his magnificent home furnished by the Carlsberg Brewery, and he played Santa Claus for these children every Christmas. However, maybe I should tell you that when it came to scientific things, he was very stubborn. For example, we once had a visitor, Professor Blatt, who was a famous nuclear physicist. Some of you might know the book Blatt and Weisskopf, a famous physics text. And Blatt came to give a lecture on superconductivity. This was before it had been explained by our own Schrieffer together with Bardeen and Cooper. So Professor Bohr, who wasn't so often at the Institute those days because he was head of the Danish Atomic Energy Commission, came personally to introduce Blatt. And he said how very pleased we are to have this brilliant physicist here to tell us about superconductivity, and introduced him in a very nice way. So then Professor Blatt began to lecture. And after about 15 minutes, Professor Bohr got up in a very halting, kind of apologetic way, said how grateful they were to have this famous physicist here to tell us about superconductivity, but he wonders if he has taken into account appropriately the interactions of the electrons. And he wrote a few things on the board and sat down. Then Blatt went on just as if Bohr had said nothing. And in about 5 minutes or so, Bohr got up again. And again, he kind of apologized, and after thanking him for coming and so on, he said he wonders if they have taken into account appropriately the interaction of the electrons. Again, Blatt went on as if nothing had happened. So for a third time, Bohr went through this procedure. This time, Blatt said, if I'm interrupted again, I'll have to stop. So in just about 2 minutes, Bohr was on his feet again, saying we're pleased to have him, but he wonders if he has considered appropriately the interaction of the electrons. Bohr sat down, Blatt sat down, and the seminar was over. That's probably a little faster than the seminar today. Okay, so anyway, I just told you that Bohr had figured out that it was uranium-235 present in only one part in 140, which was responsible for fission. At about this same time, people did experiments, and they're able to show that 2 or 3 neutrons were given off with each fission. That meant that it was possible to have a self-sustaining chain reaction and to have a bomb or a tremendous energy source, perhaps. So with this idea in mind, Albert Einstein wrote a letter to President Roosevelt urging that a crash program be undertaken to develop an atom bomb before the Germans, who had discovered fission, got there first. The next transparency shows Albert Einstein together with Lyman Briggs, who was the Bureau of Standards, the man who was appointed by Einstein to decide whether or not to do this. It took Roosevelt fairly long to do this, but he finally succeeded, and they decided it was appropriate to go ahead and do a crash program. Now I want to go back to Harold Urey. It was recognized that if they were going to do this, one of the ways they needed to proceed was to be able to separate uranium-235 from uranium-238. And because Harold Urey had won a Nobel Prize for separating isotopes, he was thought of as the ideal man to lead this project. And that's exactly what he did at Columbia University. Well, I've already told you a little bit about him, but now let me tell you a little bit about how he was as a scientist. I got to know him at Chicago, as I said. Urey had extremely broad interests. I've already told you about his interest in separating isotopes for which he won the Nobel Prize. He also developed what was called the Urey-Bradley potential. It was a potential energy surface, which Mike Kasha would know all about, for molecules, really. He also developed something that was very important in the early ideas of how evolution might have gotten started. He had the idea that if you took ordinary inorganic chemicals and put them together with electricity or heat, things like hydrogen or carbon dioxide or maybe carbon monoxide or methane and ammonia, that you would get the byproducts, not the raw products, for evolution. You would get amino acids and some of the other species. That was done together with his student Miller. And he also was interested in the geology of the moon. Since we were sending people to the moon, he thought it would be very interesting to predict what the surface of the moon was like. But now the important point. Although he had these broad interests, you would think he might go from one to the other. As he hit his head on the wall with one of them, he'd go to another, back and forth. That was not at all true. When he was studying one thing, he studied it to the exclusion of everything else, and he studied it on and on and on, ad infinitum. Okay. Well, under Harold Urey's direction, 3 different methods of separating uranium-235 from uranium-238 were undertaken. 2 of those methods produced such a small amount of uranium-235, although very pure, that they were fairly soon discarded. The other method was the gaseous diffusion of uranium hexafluoride. That happened to be the one I worked on. And I have a slide here which describes very briefly the idea. What you do is you take the uranium consisting of these 2 isotopes, especially, and make a gas, uranium hexafluoride of it. And then you make it diffuse through tiny orifices. And the uranium hexafluoride U-235 diffuses faster because of its smaller mass. Now, if you wanted to get uranium-235, which is 90%, say uranium-235, and you start out with only 1 part in 140, you need to get a total separation factor of 9 times 140, which is 1,260. And the separation factor you get from a single pass through the orifice is just alpha. You can look it up in any physical chemistry book, the square root of the ratio of the masses, which is 1.0043. So you can see that you need to make a tremendous number of diffusions before you get anything at all pure. It's an extremely tedious, difficult process, and it takes a huge plant, shown on the next transparency. This is the plant at Oak Ridge, Tennessee, which went under the code name during the war because it was so secret, K-25. And it occupied something like 40 acres. So it was really a huge thing. Now at Columbia, as I said, I worked on this project, and my particular part of the project was to test the corrosiveness of uranium hexafluoride. So I built a kind of pilot plant which circulated uranium hexafluoride around and around and around and looked at the corrosion and the erosion of the uranium hexafluoride. In fact, I remember thinking at that time, why did I study chemistry? I should have studied plumbing. Anyway, I should probably also tell you about how this was at this time. You know, there was incredibly intense security. And the main way that security worked was they They had each little group with its own particular problem working, but there was no contact between any of those groups, so that nobody knew really what they were doing. We didn't know what we were doing at all for a long time. There were all sorts of weird rumors, and finally the head of our group illegally told us what we were doing. One other thing, I went to Colombia in January 1943, and in July of that year, I got drafted into the Army. The Army itself sent a Captain Grochens to my Board of Appeals in Columbus, Ohio, to tell them they should not draft me because I was very important to the war effort. Well, the people at the draft board, they said to Captain Grochens, "What is he doing that's so important?" And Captain Grochens said, "Well, I don't even know myself, but it's very, very secret." And so the draft board said, "Well, we have draft quotas to fill, and if you can't tell us, we'll draft him." So I was drafted. I was told by the Army, whatever you do, stay in the Army. Don't go into any of the other services like the Army, the Navy or Air Force or something like that. Well, I took tests when I got into the Army. I think everybody did, and I did well on them. So I was offered commissions in both the Air Corps and in the Navy. And the officers who offered these to me were absolutely astounded when I turned them down. All right. Now, an alternative to the production of uranium-35 was developed by Fermi. And it was his original idea. Here it is on a transparency. If you bombard uranium-238 with neutrons, you make uranium-239. And the uranium-239 beta decays in 2 successive steps, giving 2 new elements, neptunium and plutonium. The neptunium is very short-lived, about a day or so, and the plutonium is about 24,000 years. If you note, the plutonium is just 1 alpha particle, 2 protons and 2 neutrons, heavier than the uranium-235, so it was believed that it would be fissionable, and sure enough it was. You may say, well, if this was right, Fermi had the right idea to begin with, why did he have all this trouble? Why was he wrong? Well, it turns out that uranium-235 fissions with such a high cross-section that all the activities which Fermi saw were radioactive fission products and not this process. But anyway, underneath the football stands at Chicago, University of Chicago, Fermi built a reactor to produce plutonium to test out this idea. And he was able to produce plutonium. The exciting thing about this is that the plutonium now is another element and is therefore fairly easy to separate chemically from the uranium. So you don't have to go through this terribly tedious isotope separation. Nonetheless, both procedures proceeded. We had this big K25 plant, so uranium-235 and plutonium-239 were both made. Let me tell you a bit more about Fermi. I got to know him fairly well at Chicago after the war. But he was at Los Alamos. In fact, at Los Alamos at this time, was the greatest gathering of scientists probably has ever occurred and may ever occur. It was an incredible gathering of scientists. But anyway, at the University of Chicago, Fermi had a kind of informal seminar every Friday afternoon, and people would come together, and he would point to somebody and say, what have you been doing recently? Tell us, you know. And so at the beginning of each period, when Fermi was getting ready to choose somebody, the graduate students and the young faculty were all ducking down, trying not to be called. Anyway, on Enrico Fermi asked Maria Mayer what she had been doing to tell us about her magic numbers. She had published an article on magic numbers in 1948 in Physical Review. What she found is that certain numbers of neutrons and protons, namely 2, 8, 20, she didn't have 28, 50, 82, and 126, neutrons and protons were unusually stable. And on this particular day that Fermi called on her, she said, I have found, using a quantum mechanical particle in a box, a way to explain some of these magic numbers. She didn't use the harmonic oscillator, she used the square well, the particle in a box. That I can get 2, 8, and 20, but then I get 40 instead of 50, 70 instead of 82, and 112 instead of 126. And she said, you know, the surprising thing about that is that there's a sequence in the differences, 10, 12, and 14. And so everybody was kind of discussing this, and there was a model by Malenka, which had a line model potential, which could maybe explain 50. And fairly late in the discussion, Enrico Fermi said something which passed right over all of our heads, but it shows his incredible brilliance. He made a very simple statement and didn't augment it. He simply said, why is it that spin-orbit coupling should be so strong in nuclei? You see, he had already recognized that it was strong spin-orbit coupling that was involved, and he went to the next question. Why is it so strong and so much stronger in nuclei, say, than in atoms? Well, anyway, if we're able to make, as we are, say, plutonium-239 and uranium-235, it's necessary then to somehow make a bomb. You may be interested in the mindset of the scientists who are working on this project. He worked extremely hard, probably 60 hours a week or more. And the reason was that we were convinced that Hitler had a good chance of getting there first. In fact, Hitler was making speeches all the time, and we were hearing what his speeches said. For example, he was saying they had at that time a buzz bomb, which was a plane loaded with explosives which would go over to England and drop and explode. It was called the B-1. And Hitler was saying, I have a much more destructive weapon. And we were sure he was talking about the atom bomb. But in fact, he was really talking about the B-2, the rocket bombs. And they never really came that close, as we found out after the war. But at the time, as far as we knew, they might be very close. Meanwhile, in May of 1945, I moved from Columbia University briefly to Oak Ridge and then to Los Alamos. I arrived there, as it turns out, just 2 days before the test of the first atom bomb in Alamogordo. And I have, maybe after the thing, I can show you samples of the glass that were produced when the first atom bomb was exploded in Alamogordo on the sand of the desert. It's a sort of glass coming from the tremendous heat of the atom bomb. Two methods have been used to try to develop an atom bomb. They were sort of the genius of Oppenheimer, shown here together with Leslie Groves. I'd like to tell you a little bit about those two men because they were quite impressive. Oppenheimer himself was an incredible scholar. He knew everything. like. He, for example, read Sanskrit, and he was perhaps the second really great theoretical physicist in the United States after Gibbs. Furthermore, he had amazing ability to get along well with people. He sort of held them in the palm of his hands almost. If he wanted to impress you, most people, when they want to impress you, they're getting excited, they speak louder and louder, the way I do, I guess. Oppenheimer did precisely the opposite. If he wanted to make a point, he lowered his voice so that everybody would lean forward to be sure to hear what he was saying. In some way, Oppenheimer at the end was a fairly tragic figure because his clearance was taken away, and I'll talk about that a little bit later. Gerald Rose was an entirely different kind of man. He was an engineer. He didn't really know very much science. He was, however, amazing in some regards because he picked up Oppenheimer. That's incredible that he chose him, because Oppenheimer had several things against him. The security people were very much against having Oppenheimer available for the director of Los Alamos. Okay. To give you some idea of Rose, he was really a military man, and he thought he could treat scientists just like military people, but little by little he found out that wouldn't work. I remember, it shows how immature I was in some way, a group of us in the tech area where it was illegal to salute because it was dangerous. You might be carrying radioactive material around or something. A group of us lined up in a line and marched right over General Groves and did not salute. Okay, after the war, General Groves got his legs. As soon as Japan surrendered, all of a sudden, we had inspections and all the all of being in a real army. The two methods that were developed at Los Alamos for exploding the atom bomb, I'll talk about now. The first is called the gun mechanism. In it, a piece of non-critical uranium, that's something that by itself will not explode, is driven by an explosive charge into an annulus of another piece which is also non-critical. When the two come together, you produce a critical amount and the thing will explode. This is, in fact, the mechanism and the material with uranium-235 that was used on Hiroshima. I think there's nothing in between. That's perfectly how that could work. Okay, the second mechanism, and the one which I worked on at Los Alamos, is sometimes called the snowball mechanism. Because it's like squeezing a snowball. The idea is that you have a series of shaped charges around a spherical piece of plutonium or uranium. In fact, the one that was plutonium-239 was what was used. And whereas the sphere before explosion was not critical, it was very near critical. And by squeezing it, making it smaller, you actually produce a critical mass, and it will explode. And now I come to one of the parts of my talk, which is sort of especially difficult to tell you about. The decision had to be made on whether or not to drop the atom bomb on Hiroshima and Nagasaki. And certainly some of the scientists at Los Alamos, I was among them, preferred that we try to have a demonstration on a deserted island to show the Japanese the force of the atom bomb in the hope that they would then surrender. However, what I didn't know, and I think most of my colleagues there didn't know, is that at that time there were only 2 or 3 atom bombs available. So in some sense, what we were doing was a big bluff. I mean, although others would be coming, at that exact time there were very few atom bombs available. So Truman, who was president by now, Roosevelt died of a heart attack, had to make the decision, and he made the decision to drop the bomb on Hiroshima. The test of the snowball mechanism occurred July 16th, 1945, and the Hiroshima bomb, the gun type, was dropped on Hiroshima August 6th, 1945. These are the people who flew the Enola Gay, about which there's been a lot of controversy. This is the Enola Gay. There's been this controversy at the Smithsonian Institute. And about 125,000 people were killed at Hiroshima. Here's a picture of some of the devastation. Well, the Japanese didn't surrender right after Hiroshima. And 3 days later, the other bomb, the snowball mechanism, sometimes it's called the Fat Man, here it is, was dropped on Nagasaki. Well, you know, it's easy to rationalize that we save lives by dropping these 2 bombs and killing 250,000 people. Because if we had to go from island to island and invade the homeland of Japan, it's hard to say how many lives would have been lost. Of course, we can't know how soon the Japanese would have surrendered. And I've talked to many different people, servicemen, talked to somebody just today, who say, I would be here if the bomb hadn't been dropped. So it's difficult to know whether the United States was right or not. I certainly cannot fault Truman. He had all the facts. But I personally, and I know other scientists like me, will always carry a sense of guilt because of what happened. Let me go on to tell you something about that happened after this. Of course, the atom bomb was not the end of things. The atom bomb became just the fumes to the hydrogen bomb. That work was done, developed essentially by Stan Ulam and by Edward Teller, shown here with Doris Granberry, who took over at Los Alamos after Oppenheimer left. Now, I'll tell you just a bit about Edward Teller. I got to know him fairly well when I consulted for the Chancellor of the University of California system. We were to give advice on the operation of Los Alamos and Livermore and some of the other laboratories. Teller was an incredibly brilliant man. He had idea after idea, just tossed them off like nothing. On the other hand, Enrico Fermi would knock them down one after the other just about as fast as they came out. And Teller didn't appreciate that very much, I can tell you that. But you know, if you have only one good idea out of maybe 50 or 100, that's good enough. So he was really brilliant. On the other hand, he was, I would say he was obsessed with a fear of Russia. And so he was absolutely determined that we should build the hydrogen bomb. And when Oppenheimer drug his feet, Teller was tremendously upset, and it was partly as a result of this that Teller testified in the security clearance hearings for Oppenheimer. Oppenheimer lost his security clearance and became a sort of tragic figure, a guy who was revered by most of American physicists. On the other hand, Teller, having testified against him, was sort of persona non grata. He was, and still is, I think, looked down on by many American physicists. What happens in the hydrogen bomb, of course, is that initially it was called a device. In fact, it was called the super before it was called the hydrogen bomb. And initially, the idea was to fuse deuterium and tritium to make helium-4 and a neutron and give off sort of unlimited amounts of energy. In fact, we know that because you have to put together a critical amount, but you can't have that amount to begin with for an atom bomb. The size of an atom bomb is definitely limited by how much you can put together simultaneously that is not initially critical. On the other hand, the hydrogen bomb is unlimited in some sense because once the atom bomb ignites it, any amount of fusible material can be set off. It turns out that shortly after the initial idea of using tritium and deuterium, hydrogen 3 and hydrogen 2, it was recognized that lithium 6 deuteride was a much better fusible material. However, the fact that you can use unlimited explosive power with the hydrogen bomb leads to a new dilemma far beyond the realm of science. And it's what I want to finish talking about today. It is possible, or close to the realm of possibility, for man to commit global suicide with what is called the hydrogen, what is called the cobalt bomb or the hydrogen bomb. This is shown on the last transparency, and it is hypothetical. It's never been built. It's something, however, which is certainly within the range of imagination. So let me tell you about it. The cobalt bomb begins with an atom bomb as a fuse, an explosion, something to heat up. You use, for example, 3 tons of tritium, 2 tons of deuterium, and you get a reaction, tritium plus deuterium, helium-4 plus neutrons. So you get a ton of neutrons if you start with 3 tons of tritium and 3 tons of deuterium. Now you surround this hydrogen bomb with a blanket of cobalt. Cobalt 59, you would need 59 tons, according to the simple equation, to react with the 1 ton of neutrons to give you 60 tons of cobalt 60. That cobalt 60 is enough. Is spread evenly over the surface of the Earth to kill everything, with the possible exception of some insects, particularly the cockroach, which is particularly capable of sustaining radiation. They live in reactors, and they do surprisingly well in very high fields of radiation. give you some caveats about this cobalt bomb. First of all, it would tend to blow into outer, if you just shoot it off in the atmosphere, it would blow into outer space, and most of the cobalt-60 would be dissipated in space. So if you're really going to use this effectively, you would have to shoot it out deep in a mountain so that it couldn't blow completely into outer space. Secondly, of course, there's always meteorology. Rainstorms would make much more of the activity come down some places than others. Wind direction, all of this would be important. So perhaps we would only come to the verge of committing global suicide. But you must also recognize that this is not the only way we can commit global suicide. Bacteriological weapons might be easier, maybe even better. So we are getting close to the time when we really could commit global suicide. But you say to me, no one would do this. Who would want to commit suicide? That's absurd. But think for a second about Hitler hiding under Berlin at the end of World War II. He was already committed, I think, to suicide. I believe that he would have taken a sort of perverse joy in taking everybody with him if he could have. He even made speeches to say that he would tear down Europe for 1,000 years to come. What then is the answer to this dilemma? You cannot guarantee that the human race will not produce other Hitlers. They almost certainly already exist in the 5 to 6 billion people on this earth. Fortunately, they don't have the power which Hitler held. In all honesty, I don't really know the answer to this dilemma. You know, it's interesting. In the scientific realm, we can expect our students to climb on the backs of a Newton or an Einstein, Dirac, or a Schrieffer, and go on from there to greater heights in science. That is because science is a rational kind of structure. However, in the realm of ethics and morality, you cannot climb on the backs of a Jesus, or a Mohammed, or a Gandhi. We cannot be handed our morality on a silver platter, the way our greatest scientists have handed us their knowledge. This, then, achieving the kind of morality that can allow our world to continue is our greatest challenge. Thank you.
Should have any questions in the audience? Yes.
When you were working for the project, when did you know it?
Yes, that's a good question. The question was, you were working on the project, what did you know and when did you know it? When I came to Columbia University, I knew nothing. The way of security was to have each small project totally separate from every other one, so that nobody knew what the other people were doing, and it was very difficult to find out what was going on. However, I had talked with lots of other people, and there was considerable discussions of what was going on. We had some ideas. We weren't really sure that they were right at all. In fact, some of them were wrong. However, the head of our group, a man by the name of Homer Priest, called us all together and said, I'm not supposed to do this, but I'm going to tell you. grew up, talked to my parents, asking what was going on, because several of them had been contacted about me. So there was the FBI and CIA was certainly involved. It wasn't existent then? Okay. Yes, I have seen Klaus Fuchs. I didn't know him personally. He was a quite able scientist, highly thought of. He'd been in Britain before he came to the United States.
You were at Los Alamos.
Yes. Yes.
What was the situation
Well, they still attempted to keep it compartmentalized until after the war. As a matter of fact, after the bomb drop on Alamogordo, this is kind of a security breach. I got this piece of fused sand. This is from the first atom bomb blast, and it's a sort of glass which occurs because of the tremendous heat from the atom bomb. It's sort of greenish gray. You can look at it, some of you. Yes, it's still somewhat radioactive, not dangerously so at all. Yes.
At the time of the first test of the atom bomb, didn't Oppenheimer and others have a contest as to whether or not it would spread across the world?
Yes, I can tell you.
Dr. Rossi on my left there at the first atom bomb explosion, and we have no attention.
Yes, I can tell you. I don't know whether this is. I have to first say I was not at the first atom bomb explosion. I was in Los Alamos, but not at the atom bomb explosion. But so I don't know for sure what I'm telling you is correct, but I know what people said. It was said, in kind of in a joking way, that Fermi, not Oppenheimer, but Fermi and Teller had a bet that whether or not the atom bomb would ignite the atmosphere. And Fermi bet that it would not, and Teller bet that it would, and of course, only Fermi could win.
Do you believe that a project of this scope could be conducted today?
I think it probably could not be conducted as secretly today. People, of course,